Hi my dear friends, it was a while since I made my last video clips, and this I feel it was very important for continue on, because after when I saw the test in Hadron Colliders, I was thrilled and I was so happy, that I said, what, I have to continue on, and share all the good information I was able to obtain to begin with. I want to thank all the scientists and all the people who build that, all the scientists who worked Hadron Collider, and all the people who build that remarkable structure. And I knew all this about probably 15 years ago, but I was kind of hesitating explain this because when you get into uncharted territory, there's like the humankind doesn't have an instrument to go too low that point, and try to understand how everything happened, start from the scratch. And again, I said thankfully, that the test, when I saw what happened, I knew then that I was right on the money. Okay, let's start, exactly how the atom forms. What I saw, I'll explain you according what the test I saw, according what I saw the test, I saw that I always was predicting that the mass particles, they are way smaller than the nucleus itself. And what I saw in the Hadron Collider, it was exactly what I was expecting to see. And how the mass particles, they get that small to begin with. Can you imagine the mass particles? They are just a small fraction of the energy what the nucleus contains itself. How I end up in that conclusion, because one time I took the magnet and started to break it and break it and break it. No matter how much I break the magnet, I keep realizing that no matter how much you break it, the magnet always will have a negative and positive ends. If one side is negative, the other one automatically is positive. And I start to calculate, and start to break it down even more when there's already no mass to break it down, how far it will go. I realized that, because I know already the energy, even it's a ghost particle, but it has a strength to it. And, the only way the energy is energy, it's only when it vibrates or it shatters. Otherwise, the energy is not energy. What the universe produces is not an energy at all. It's a ghost particle, and how that ghost particle turn into energy. You see, when the energy, why, the scientists cannot detect any energy out of the space. The one thing that, the energy production is so small, a tiny amount of that, it's undetectable. Think of this, even that the proton, they cannot actually detect the energy which one it's produced by the space itself. Though you see what happened, when the space produced that energy, because they're so small, they cannot actually vibrate or shatter. And what happened? And actually, as soon as another small chunk of energy comes, they hold each other and they freeze. They don't freeze actually; they harden. Because freezing, to say that actually wrong word to use, they actually harden immediately. And what happened now? The two particles, even they don't move, they don't shatter, they don't vibrate, but they're like a tiny neodymium magnets of the space. And they start, anything space produces, they absorb and absorb and absorb and absorb, constantly, non-stop. What happened? Because they cannot share, they can absorb that energy, and they release that energy. And when you have so many of them in a small area, and they absorb the energy from space, and they like multiplying it, like the space particle, the mass particle, they're like a step-up transformers. What they do when they absorb the energy the space produces, what happens, they within them, they like conjoin and they join and they become a strength, they become an energy. When the whatever they like the mass particle, they absorb ghost particle and they release energy out. And this energy, when so many particles simultaneously, they release energy constantly, and that energy accumulate, they start to pull each other until they form electron itself. And what happened now? Imagine continuously that going on and on and on and on. You see, and the electron, obviously, it's already energy itself. And what happened? The energy start to vibrate, and as long as it vibrates, it you see, they dissolve into the space. In the vibration, that energy dissolved. The only way energy dissolve back into the space with the vibration. If it doesn't vibrate, the energy will stay like that for billions of years. As long as it's vibrating, it will dissolve that energy back into the space. Now imagine when it's vibrating, it constantly it absorbing more and more and more energy. And but because there's so many more mass particles than the electron itself, the production is more than it can handle. It start to absorb more, and it goes inward, until it start to build that the quarks itself. And this is how think of this, from the scratch, how the atoms then form. When I saw the test, in the Hadron Colliders, that 99.8%, it's hard to see, exactly what happened to them. Why? Because, not all molecules, they have the same amount of energy. And some of them, they have more, some have less. And plus, what exactly gave me the clue that, how the particles they form. And I say I knew that, but it was hard for me. I was kind of hesitating to explain that, just for one reason, because I wasn't sure, how small do particles go. With my calculation, they should be, like a small fraction of what the nucleus it was. And actually, that was the exact what I was expecting to see. And when you look at the background shot of that Hadron Collider, you see, what I saw, there were long lines. The long lines actually represent, high concentration of the energy, and the short lines, those short lines, they represent, small concentration of energy. And imagine because the nucleus is the one what it absorbs the most energy. Because it's larger and it can absorb more energy, because it constantly, it dissolves the energy back into the space, and it need more to survive, to have existence as an energy particle. And now this one, again I said, this it should, you see, I said the only way the particles, they will harden, when they are extremely small fraction size of the nucleus itself. And as long as they can shatter or vibrate, the energy, the ghost particle, actually I named it, as a genesis, the beginning of the particle, because that's how it starts. It doesn't start as energy the way, some scientists, they think, it started with the Big Bang, there was trillions of degree heat or what. No, they don't. You see, they start to produce heat when they accumulate and become formations. Then they produce heat. They don't produce heat, when you go into the dark parts of the universe, there is no heat at all. There is nothing exists. The space doesn't have anything to produce heat or cold. The cold and the temperature changes come with the energy itself. Okay, it's that simple. You cannot freeze the energy. You cannot, even with heat, you cannot destroy the energy. The only way the energy, it dissolves itself when it shatters. When it shatters, it slowly dissolves back into the space. There's also certain ways, you can destroy the energy too. With fires, with explosion, that what happened, the energy doesn't recycle itself. It recycles when it turns liquid. Now this is another thing already we have to go into it. Now let's see how you see the molecules, they turn into gas particles, they turn into water. What exactly is water? Some of you may wonder, for long you have been wondering. Think about this, what the water made of. Two particles, hydrogen, and one particle, oxygen. And look at, in my previous video clips, I clearly explained. You see, the energy speed increases according by the size of the energy concentration. Now, smaller they are, slower they are. The bigger they are, faster they gain. The faster they move. Imagine two small. You see, the slowest particle, which one is the hydrogen, they get pulled by the oxygen, because oxygen is like constantly hungry for more energy. When they pull, what they do, they suddenly force the oxygen to slow down. There's no water over there. That's the energy itself. What you're looking at when we're looking into the water, we're looking at the slow motion of the atoms function. That's all what it is. It's like a mirage in the desert. This is what we're looking into when we're looking into the water. And you would grab your hand. I mean, look at it and look at it. It's, for a long period of time, I was trying to understand what the hell is this, the water, until I was able to completely understand how everything is formed. This is another step now, how I was able to understand how carbon dioxide, they affecting our weather pattern. Think about this. You see, when we breathe in oxygen, we breathe out carbon dioxide. What happens? Our body take the you see, energy part of the oxygen, but it doesn't take the mass part of the oxygen. And what happens when we breathe out carbon dioxide? This particle actually end up with more mass than you see the normal particles they should have. You see, that's what. And again, I said, as long as it's not vibrating, it cannot absorb heat. And what it does, it releases heat, but it cannot absorb heat. As long as it vibrates, it's energy. If it doesn't vibrate, then it's you see, it's a hard particle. It's the mass itself. And the mass, because it cannot vibrate, it cannot release heat, and it actually absorbs heat. And this is how, when the sun photon, they strike carbon dioxide, they absorb heat fast. Excuse me. They absorb heat faster than other particles like the oxygen or others, because I said, you see, when electrons, they're revolving around, they're cooling down those mass particles, which when they just the end of their you see, energy concentration itself, the end of their formation, and constantly those mass particles, like a crazy, they're revolving the same way, just like the electrons themselves. And they, even though get struck by the photon, but they cool down also at the same time. But when they have more than more mass particle than the electrons, they don't cool down fast enough. And this is what exactly does the carbon dioxide to our atmosphere. I hope, my friends, all this explanation will be good enough until my next explanation, and hopefully the next explanation will go in the burning question, which one we call the life itself.